Hi, my name's Will Krosick, Scientific Services Manager at Chemical Computing Group. Today I'd like to demonstrate how to perform a conformational search using LowModeMD to explore the movement of a flexible loop believed to have an important role in activity. So let's get started. Here we're working with a row kinase. The structure is actually a homodimer that's been superposed so that we can see the variability in the p-loop. We have the extended conformation shown in orange and the folded or the dangling conformation shown in cyan, which allows interaction with the ligand. In the next steps, we're going to use LowModeMD to investigate the movement of this loop, modelling the transition from the extended through to the folded conformations. So first, I'm just going to hide and make inert that folded conformation as well as hiding the ligand. Now, since our focus is on the p-loop itself, we can fix atoms further away for computational efficiency. The file has already been prepared, first using the default settings of Quick Prep, but also with sets or collections of atoms created so that we can easily define which parts of the system we want to remain mobile, which are fixed, and which should be inert. So if I just expand this, I'll select the fixed set and I'll fix those. Let me just render those green. And then I'm going to select the inert set and I will make these inert, rendering them in white. Now if I just zoom out a little bit, you can see that in effect we've created shells of atoms. The white shell represents the atoms that are both fixed and inert, and these atoms, we're doing this because these atoms are far away from the action. The green shell represents the atoms that are fixed. That's because these residues are nearby, they've got fixed coordinates that can interact with the region of interest. And then finally, we've got the orange shell representing those atoms that are free to move for the region of interest itself. Using this approach of setting up the shells can significantly speed up our search. And with that, we can now perform our conformational search. So I'll just open the panel, which is suitable for generating conformations of proteins, peptides, macrocycles, DNA, or RNA. At the top, we can specify what we want to explore the conformation of, and the lower portions of the panel control the conformational search method itself, together with options as to when the search will terminate, and the energy window, which sets the limits on the potential energy of the resulting conformations. So I'm just going to make some changes. I'll start by changing the RMS gradient to 0.1. This will stop the energy minimization process when the root mean square gradient falls below this value. I'm doing this because I want to generate a lot of conformations and I want to generate them quickly. The other key value to change would be this energy window. This is an important parameter to adjust depending on whether we're working on a small molecule or something larger like a peptide or even a larger protein or antibody. In today's example, I'll want quite a wide energy window so that I can preserve all of the conformations that we generate. So I'm just going to push that value up a little bit. And with that, I can press OK to start the search. You'll see a database viewer has been opened where the results will be written, but I just want to take a moment to go back to our panel to explain some of the additional options. Today we're using the LowModeMD algorithm. This is a combination of MD and low-mode search. It's suitable for generating conformations of macrocycles, protein loops, or small molecules, including explicit waters and or counter-ion search. LowModeMD is efficient to perturb the molecular systems along the low-frequency vibrational modes. We can add ligands and cofactors with little additional overhead. Mo will first generate random initial atomic velocities with kinetic energy concentrated on the low modes. It will then perform NVT dynamics for 0.5 picoseconds at 300 Kelvin, and then the system gets minimized. And that process gets repeated to sample for other minima. It will be saved to the output database if the strain energy is permitted, as defined in the energy window. If so, Mo will then check to see if the conformation is unique, as specified here in the RMSD limit window. And it will repeat until the stopping criteria are met, which are defined here. A key advantage to using LowModeMD is that it's an efficient sampling of the conformational space using angle and dihedral-like motions. And for that reason, LowModeMD is the recommended approach for both large and complex structures like macrocycles and protein loops, but also detailed small molecule analysis. However, chiral inversions as well as amide and double bond rotations rarely happen. If that's what we want to see, we might want to consider one of these other options. So other options in this panel include what we want to explore the conformations of. So currently it's set to whatever is in the main Mo window, but we could also specify a database which could contain multiple structures. In today's example, we define sets or collections of atoms to determine which parts of the system should be fixed, mobile or inert, but the other option would be to use the rigid bodies, and they can be specified using named sets, tags, or detected protein domains. Finally, there's the option that we could use the refined output as our input to further refine with QM optimization. So I see we've got quite a few results in our output database, so I'm just going to close the panel and I'll cancel that search. And we see the results are stored here in the database viewer, a chemically aware spreadsheet that actually contains a wireframe of the conformations that we've just generated, together with some useful descriptors, including the radius of gyration, this chi value, which is encoding stereochemistry information, our potential energy, as well as the potential energy relative to the lowest energy conformation. So I'm just going to select all of these and I'm going to send them to Mo. I'll go back to the main Mo window and I'll just bring back the extended conformation. I'll want to hide our receptor, and then to focus in on the region of interest, I'm going to go to the sequence editor, which, as the name suggests, allows us to edit the sequence, as well as our launching point to various protein modeling tools, including the loop modeler if we wanted to model a missing loop. I'm just going to use the sequence editor to identify our region of interest, so I'll switch to the single letter code, and I'm just going to select that region of interest, and I'm going to extend to the entire column so that I can render our ribbon using the line style. And then I'm going to select our residue of interest, the phenylalanine, and again I'm going to extend to that entire column and then show the selected. Perhaps I'll also just hide our hydrogens so that we can focus in on that region of interest. And with that, you can see that using conformational search, we're able to see that transition from the extended to the folded conformations. And with that, it brings us to the end of today's session, where we generated conformations of the mobile P-loop using LowModeMD. Classical MD would not be able to explore this amount of conformational space in such a short time. If you have any questions, please do reach out to us at support@chemcomp.com.